Imagine a world of high-precision manufacturing. We're talking millions of perfect copies, born every single second. A whole universe of gleaming, flawless metal, shaped with just impossible speed and accuracy. But then, something goes wrong. In the ghost of the machine, some tiny deviation, an error you can't even see, creates this strange and really costly anomaly, a defect, and it completely interrupts that perfect rhythm of production.
Okay, so let's get into it. We're basically going on an investigation here, a hunt for an invisible saboteur in the super high-stakes world of metal forming.
So our story starts with a process called deep drawing. And honestly, it's an engineering marvel. You take a flat sheet of metal, and with just immense force, you punch it into a perfect three-dimensional shape. It's incredibly fast, super efficient, and it gets rid of the need for expensive welding and machining. But, this process has a dark side. There's this hidden flaw that just kind of emerges from the very properties of the metal itself, and it totally disrupts that flow of perfection we were just talking about. So let's meet our antagonist. It's called earring. You can see it right there. Instead of a perfectly clean, flat rim, the process creates these unwanted, wavy, ear-like lobes. Now, it might not look like much, but in a world of microscopic precision, this thing is a costly villain. And this quote right here, it gets right to the heart of the cost. Every single one of those little ears has to be precisely machined off. I mean, that's a whole other step in the process. It's more time on the clock, it's wasted material, and it's money just draining away, all because of this one persistent defect. So the big question is, how do we stop it? Well, to defeat the enemy, you first have to understand it. So it's time to line up the suspects responsible for this earring defect. All right, think of this slide like our detective's evidence board. Engineers have a whole list of suspects. It could be something called planar anisotropy, which, yeah, is a fancy term, but it just means the metal has different strengths in different directions, kind of like how wood has a grain. Or, it could be something simpler. Too much friction, the wrong amount of clearance between the tools, or maybe the force holding the metal down. But the researchers on this, they decided to focus their investigation on one prime suspect, the shape of the raw material itself. The theory was pretty simple. If the problem starts with the shape of the metal going in, then maybe, just maybe, the solution lies in changing that shape. Now, before you start wasting a single piece of real steel, you take the fight to a virtual proving ground. Yeah, it is time to run the simulation. And their weapon is this piece of really powerful software called DEFORM 3D. Think of it like a digital crystal ball. It lets them simulate the intense pressures of the deep drawing process and predict exactly how the metal is going to behave, and, more importantly, how our antagonist earring is going to form. The whole process is really this high-tech cat and mouse game. They build the entire setup virtually, every tool, every piece of metal. Then they apply all the digital forces, the speed, the incredible pressure, running it step by agonizing step, all to predict the enemy's next move and design the perfect trap. And here you have it, the results from that digital battlefield. On the left, you see the standard circular blank. The simulation predicts a 12% earring defect. That's a clear failure. But on the right, you've got this new modified shape. By strategically trimming the blank, the simulation predicts the defect will drop to just 8%. That is a potential victory. Okay, so a digital victory is one thing, but honestly, it doesn't mean anything until it's tested in the real world. The theory now has to face the fire and pressure of physical reality. So based on that successful simulation, the engineers go and create the physical blank. The optimized shape, which was once just data on a screen, is now cold, hard steel, and it is ready for the press.
This is it. This is the moment of truth. The digital prediction was a success, sure, but theory is clean and it's perfect. The real world's not so much. Will the modified blank actually survive the incredible forces of the deep drawing press, or is that flaw going to find a way to reappear?
The test is complete. The press has done its work. The cups have been formed. All that's left now is to measure the evidence and deliver the final verdict.
Let's just look at the raw data for the original blank. I mean, you could see the evidence of the flaw immediately. As you go around the rim of the cup, the height varies wildly from over 28 millimeters all the way down to just over 26. That variation, that uneven edge, that is the earring defect, measured out in cold, hard numbers.
But now for the comparison. The physical results are in, and they are absolutely undeniable. The original blank produced an average earring defect of 13.4%. The new, modified blank, only 9.68%. The simulation was right. The countermeasure actually worked.
And the difference between those two results, this entire investigation, it all comes down to this one single crucial number. That number represents a nearly 28% reduction in the earring defect. By trusting their digital simulation and just modifying the shape of the blank, the engineers took on a hidden flaw and, well, through science, they beat it back.
But look closely here. The flaw was weakened, yeah, but it wasn't eliminated. The battle was won, but the war for absolute perfection, that continues. It kind of leaves you wondering, right? In this relentless pursuit, what other tiny, unseen forces are just waiting to be discovered and defeated next?